What specifically we're going to look at is when we're projecting something into the air with an initial velocity, but also at a particular angle, okay? So instead of just like throwing something straight down or something straight up, we're going to project something at an angle, like shooting a slingshot or catapulting a pumpkin or things like that, okay? What we can do, hold off on writing this down yet because I want to talk about a couple things first. What we can do with parametric equations is basically describe what's happening to the motion two different ways. We can describe what's happening horizontally, and we can describe what is happening vertically in terms of the amount of time that's passed. Okay? So instead of just having one equation that models like the height of our catapult, okay, we have, or our object that has been catapulted, we have two equations, one that represents how far our object has traveled, and one that represents the height of our object as it travels, okay? Both in terms of the third variable, t, which is time. So we can figure out how far and how high an object is after a certain amount of time. Okay. Go ahead and write up the set of parametric equations that I have up here, and then we'll go through what everything means. It's so sunny, I just wanted to keep them open as long as I could. Is that better? All the way? Do you want me to make it bigger? Just for you, Darby. They were kind of small. But aren't you all excited that the sun is shining against you?
You can open the blinds.
I'll leave it.
You still see the sun.
Okay, I would like you in your pods to discuss, don't write anything down yet, but discuss the meaning of each variable that I labeled up there in blue. Basically, anything that is in our equation, I wrote down in a list, and we're going to talk about what each of them stand for. So some of them are variables that will always change. Some of them are constants that we plug in. Okay? So go ahead and just talk about what you think those letters up there stand for.
So like if I threw something, the initial height would be like from this initial.
All right. We'll start off down here. Pod 1, what do you think about V naught?
I said maybe it was velocity.
Okay, probably something to do with velocity. I agree. Why do you think there's a little sub-zero right here?
Maybe like at the initial point.
Uh-huh. At the initial point. So this is our initial velocity. I'm probably going to call it V naught. If you say V sub-zero, okay, that sub-zero means time is zero. V naught is our initial velocity. All right, pod 2, theta.
The angle at which it's released.
Okay, angle of release. I like that. Okay, if we are hitting a baseball, at what angle are we hitting it at with that initial velocity, okay? The initial velocity and angle go hand in hand, okay? If I make contact with a baseball at a 30-degree angle, that's going to be like the motion of me swinging the bat. Pod 3, H now.
The height, the initial height.
Initial height, we have that sub-zero, again, so we're talking about initial height. All of these are constants, but they will change from problem to problem, okay? But they're constants, we plug them in and they stay there, okay? These that I'm going to go over in red, these are our variables, okay? So pod 4, what does time stand for? Oh. T is time. Glad I could give that away for you. How about X? Okay. X stands for the horizontal distance, specifically after a certain amount of time T. Okay? So if we plug in 1 for T, then the X equation is going to give us how far we've traveled after 1 second, or whatever the label is, okay? If we plug in 5, it's going to give us how far horizontally the object has traveled after 5 seconds, okay? And pod 5, what would our Y equation tell us?
The change in vertical.
Okay.
After.
So our vertical height, good. Okay, so if we plug 1 second in for T, then the Y equation will tell us how high off the ground our object is. Okay. Now, I want you to look at those equations. If we were to eliminate the parameter, and we are not going to, we're going to keep these separate, but if we were going to eliminate the parameter, what kind of an equation would we have? We'd have a quadratic. And, more specifically, if we graphed it, we'd have a parabola. And what direction would that parabola open? Down, because that t-squared is negative. So what's happening is our object is following a parabolic path. Okay, makes sense, right? Okay, we throw it with some initial velocity up, right? But then gravity is going to have to pull it down. Okay, so it's going to follow a parabolic motion. Now, you've probably done some of this kind of stuff in physics, but probably not as parametric equations, or have you seen something like this where X and Y are separate?
We did them differently. We've used the kinematic equations.
Good. Okay. Okay. So what we're going to do, I'm going to give you a scenario, and we're going to find a bunch of different things. There's 1, 2, 3, 4, 5 questions that I can ask about one scenario. And then I have a worksheet for you where we're going to do one problem together, and then the rest will be yours. Okay? So you know how to work with parametric equations. I'm not even going to ask you to eliminate the parameter. It's really about you understanding what to do with which equation. Okay? So as long as you can understand that the x represents the horizontal distance after time t, the y represents the vertical distance after time t, you're going to be able to answer any question. Okay? So, here we go. Let's just, don't write down every single word, all right? But we have a football that is kicked with an upward velocity of 30 feet per second. That's probably important for you to write down. At an angle of elevation of 55 degrees. That's probably also important. Consider the position of the ball at any time t if air resistance Doesn't matter. Okay, in physics you do that too, like air resistance, not a big deal. And for what the math that you've been doing in physics, correct? You don't worry about air resistance. Okay. So we need to set up the parametric equations. All right, so 30 feet per second. What is that going to be in our equations? V naught. 55 degrees. Okay. What about H naught? From how high off the ground are we kicking the ball? It's on the ground, which would be 0. So we don't have an initial height. All right, our initial height is 0. Okay. So when we set up our parametric equations, we have V naught cosine of theta t, and then we have negative 16t squared plus 30 sine of 55 degrees t. You're not going to write plus 0. If you do, that is fine. All right, but I want to make a point that our initial height is 0. Now, before we get into any of these calculations, I would like you to go ahead and get your calculators out and change the mode back to degree mode. If you haven't used your calculator since we played around with all those polar graphs, it's probably still in radian mode. Okay, so go ahead and change it back to degree mode for me. The next question we're going to answer, when will the ball hit the ground? So first of all, they're asking a question about when. So Gabe, what variable would we be solving for if they're asking for when? Time, okay? T is what we're going to be solving for. Now, when the ball hits the ground, is that going to deal with the x or the y equation? Turn to your neighbor and tell them x or y. Pick one.
You don't want it when it's the air. You want it when it's on the ground. And the X would be like it's on the ground. Yeah.
Kanan, what should we use? Okay, can you tell me your reasoning?
Because that's what it shows where I'm going.
Okay, so y represents our vertical height. And so if we're talking about how high off the ground or hitting the ground, we're talking about a vertical distance. So essentially, we want to take this y equation and we want our height to be 0. Now, quickly before we go to lunch, since we do not have an initial height, what's true about all of the terms over here? They all have a t. So we can factor out that t. Which tells us either time is 0. Well, we knew that because it starts at the ground. Okay, we don't really care about that one. What we care about is that negative 16t plus 30 sine of 55 degrees equals 0. When you come back from lunch, you're going to put that into your calculator for me and we'll get the time. Okay. Enjoy your lunch. I'll see you in a half hour. Okay, so you're solving this equation right here. need to know what 30 times the sine of 55 is. You move that over, divide by the negative 16. Caroline, what do you have?
I got 1.53 seconds.
Do you agree with that? Okay. Any issues getting that in your calculator? Okay. I did mean to show you what this looks like in your graphing calculator. Oops. So yesterday I showed you how to change it to parametric mode, correct? So it needs to be in degree and parametric mode. Okay, so if we plug in, what are our equations? 30 cosine of 55 times t and negative 16t squared plus 30 sine of 55 times t. If we go to graph it, you don't really see much of it, right? Okay, you can see the start of it. If you want to see all of it, let's see if this will work. We can go to zoom. There's a zoom fit. It doesn't always work fabulously, but we can try it. Did I click the right one? Okay, see, that's what I thought. It did not work the way I wanted it to. Okay. It hit the ground at 1.53 seconds, right? Okay, so we'll go back. Oh no. Okay. So we're going to go to window. We want our T-min to be if you go to window, you don't want your T-step to be too large. My T-step was like 7.5. Like that's not what I want at all. Oh. Now my calculator's thinking too hard. It's not going the way that I want it to. Zoom 6 goes to standard. You need to go to window and change your T-step. So you can change your T-step. And then I'm going to have my X's go from 0 to 30. And hopefully I can get it to fit. Oh, that wasn't beautiful, was it? Did you change your T-step to something?
Yeah, change it to 3. Like,
Change it to like 0.1. See, look at that beautiful graph. Okay, that's what's happening. So what we found is right here at time is 1.536 seconds, our graph hits the ground. Okay, so on these you're going to have to play around with your window in order to be able to see the entire curve if you want to. All right, I know there's one on your homework that I asked you to graph. Okay, all right, let's do a little bit more with this problem. Next, I want us to figure out how far does the ball travel in the horizontal direction? Does that correlate to time equaling 1.536 seconds? How does that correlate?
That's the variable you can plug in for when it hits the ground, so that's like distance time.
Okay, if our, what was it, a football? If our football hits the ground, that's how long it was in the air, correct? All right, so what we can do, since we're talking about the horizontal direction, we can take the x equation and we can plug in .536 seconds. To get 26.43 feet. Okay, so if you want to know how far it goes, you have to figure out when it's going to hit the ground first. Okay, so these parametric equations, they go hand in hand, all right? Now, at what time will the ball reach its maximum height? We're going to talk about solving this problem two different ways. Okay? If I ask for the time when the ball is at its maximum height, any ideas on what we could do to find that?
Well, if it's a parabola, it's symmetrical, so you could like take half of x and then do like your middle, and you could use that to find the y. So,
Okay, so basically, if it takes 1.536 seconds to go from ground to ground, you're saying we could just cut that in half?
yeah.
Okay. Is that logical? The rest of you. Amanda, yeah? Yeah? Okay. Will that work every time? Okay, in this example, it works. Why, Tannen? You're shaking your head.
Oh no, I was thinking like linear case.
Why would, what would be an example where it wouldn't work?
Like if it's like medium ground, it's a little more horizontal sometimes.
Okay.
False.
Okay. Okay. Darby?
Height isn't zero at the start.
Okay. This one is working out because we start and are ending at the same height. If I have an object where I hit from like 5 feet above the ground, right? And then we hit the ground, that's not going to be a symmetrical parabola, all right? If we were graphing in rectangular equations, a parabola is always symmetric. But if we're starting at a different height, okay, we're falling more, okay, it's falling faster down here than it would if we were at the same height, okay? So squishing those two answers together. So it is fine to do that if we start and end at the same height. Now, let's just say hypothetically, we didn't. How would we be able to do that? Okay? We can use the fact that our y equation is a parabola, and we know that we reach the maximum height on an upside down parabola where? Say louder.
Domain or range?
Well, domain and range refers to like all of the numbers, right? I'm referring to, yeah, that one point, the vertex, okay? So if we want the vertex, we would want t to equal negative b over 2a. Okay? And in our equation, y equals negative 16t squared plus, is it 30 sine of 55 degrees t? This is A, and that's B. Okay? So we can either take 1.536 seconds and cut it in half. That would be sufficient. Or we can say our time is at the parabola, negative b over 2a, which is 0.77 seconds. All right, one more question from this particular scenario. Now I want to find the maximum height of the football. What did we find in part D? The time of the maximum height. So what are we going to do with that time? Plug it into which one? The y equation. All right, go ahead and find me the maximum height. Nicole, what'd you get? Okay. What do we get? Oh, what would our label be? Looks like feet, right? Your labels will be an important part of this. Okay, so you need to pay attention to your velocity. I think it's always going to be feet per second. So make sure you label your time seconds and you label your distance in feet. That negative 16 t squared, that's based on acceleration in feet per second squared. So we're always going to have feet per second. All right, so I'm handing out your homework assignment, and what we're going to do is we're going to read through number 1 and we're going to do it together. Okay? So go ahead and read through number 1, and then I want you to turn to your pod and talk about ideas on how to answer the question. Okay, so first thing, let's go ahead and write the parametric equation so we know what we're dealing with. Okay, the x equation. Molly, what would our x equation be?
X equals the initial velocity times cosine theta.
Okay, and so what's our initial velocity in this case?
150 feet per second.
Okay, so we have 150 cosine of what's the angle?
20 degrees.
Okay, And then our y equation, Connor, will you help us out with that one?
-16 t squared plus the velocity initial sine of theta times plus or t plus the height.
Okay, what's our initial height?
50.
Okay, so we have these two equations. Thoughts? How do we figure out if this batter hit a home run? What are some ways,
So
Darby?
we want to see if x equals 400, y equals 20 or greater. So you can put x equal to 400 and then solve for t, and then plug that t into the y and see if y equals 100.
Okay, so Darby's idea is let's see where the ball is at 400 feet horizontally. Was there any other idea?
I was gonna say, I was thinking, I don't know.
Well, tell me what you're thinking.
Oh, like you could find, I was gonna do basically the opposite of Darby, like find where
Where's
y
20?
is 20 feet.
Okay, I wanted you to bring that up because if we find where it's 20 feet and it says like 405 feet horizontally, would that tell us if it was a home run or not? I don't, why are we leery over here?
Well, because it could be greater than 20 feet at 400, but it also could be less, and we just don't.
Okay, the ball's not going to travel through the wall, and so finding the horizontal distance isn't necessarily telling us if it's over the wall or not. Does that make sense?
Yeah.
Okay, so, here to solve too. 400 would be the distance of our wall. So we can plug that in for h. That's how far the wall is away from us. So what time does that happen at? Say louder. 2.84 seconds. Okay, that's how long it takes to reach the fence. So now if we can determine the height at that moment, we can figure out, is it hitting the fence or is it going over the fence? Okay. So our vertical distance at the time our ball is 500 feet away, 400 feet away. Okay, we can just plug that into the vertical height equation. What are we hoping for? What? We're hoping for more than 20 so it sails over the fence. What happens? You plug it in.
Oh, no.
You plug it in, Tim?
Yeah.
What do we get?
That's
What's the height? Can you give me that? 19.65 feet. Oh, man.
The angle is just a bit.
Yeah. I think I got, did you get 19? What?
13.
I got 7.4. What do you mean don't round?
So you get a 7.
Okay, so if you leave this in your calculator and use it, is that what you were saying? You get this answer? Okay. I can be a little bit close. Okay. All right. So the baseball hits probably that stripe, right, on the top of the wall, and the outfielder can get it and throw it in. probably gets at least a double out of it, hopefully, but it is not a home run.
There's a 50-50 chance.
Okay, it's not a true home. You can get a home run off of errors, right? Okay, now I want you to think about this. What if we took away that there's a fence and I want to know where this would hit the ground? Okay? When we did that in the example before, we plugged 0 in for y. When we have an initial height that is not 0, how are we going to have to solve that equation? Well, like we have this initial height here, but if I plug 0 in for y right here, like before we just factored out the t. We can't do that now. We have a quadratic with all three terms. We can only factor when it's set equal to 0. What do we do with a quadratic that has all three terms?
Oh, no.
Say it.
Ah.
Say it.
Quadratic formula.
Quadratic formula. It is possible that you will have to use a quadratic formula on your homework.
That means we will, and you're.
Yeah, you will. You're gonna use quadratic formula. I think so. Actually, I don't even remember.
6, where you have to use the quadratic formula. Yes.
She's like,
9,